Переходим к следующему докладу. Наш следующий доклад, как я уже говорил.
Okay, guys, we switch over to the next presentation, which will be delivered in English. It's a pleasure to welcome our colleague Evangelos. Evangelos, the floor is yours.
Hi, everyone. Is this the right height to hold the microphone? Is that right? Cool. My name is Evangelos Deirmentzoglou. I'm a security engineer here at Positive Technologies, based in London. And today I'm going to talk to you about blockchain consensus protocols and some security considerations we have about them. In more detail, I'm going to go through the most basic consensus protocols, proof of work and proof of stake. And we're going to cover double spending attacks, nothing at stake, and long-range attacks. First, we're going to start with some basics about the blockchain and for the protocols. What you see on the image is a basic form of a blockchain. You can see it as a vertical or horizontal, it's the same thing. It's just a series of blocks, one following the other, and it's going through one direction. What we see on the bottom, the green block, it's the genesis block. It's the block that starts everything. And what we see on with the black colored blocks is the main chain. Each block contains information from the previous blocks, and the main chain contains the one basic truth that we know about the blockchain. What you might see is some branches. The branches could be just computational occurrences. I'm sorry, should I speak louder or? Yes. Yeah, sorry about that. What you see as branches is sometimes miners could actually mine a block at the same time, or so it could be just coincidence of having a branch. Now, a branch does not consist the main chain. So any information contained in the branches, which is with the color purple, are not part of the main chain. These transactions do not consist the main chain. So anything that resides inside them is not truth. But we have the rule of the longest chain rule in the blockchain, which says that if in case any branch is longer than the main chain, it will be the main chain. So in case we have this branch right here and has two more blocks before that branch contains another block, this will be the main chain, and this will be converted into a side chain. Which means that transactions on the first three blocks, they will be invalidated. And that is up again, up until someone else mines that chain up into being the longest chain. We're going to start with proof of work. Proof of work is the main consensus protocol that is being used by most blockchains right now, most cryptocurrencies. It is used by Bitcoin, it is being used by Ethereum, and by every clone of Ethereum or Bitcoin. In proof of work, we have some miners which do some puzzles. They do those puzzles to ensure security of the network. In essence, we're ensuring the security of the network by investing in natural resources, which is electricity. So miners have, they construct rigs who do specific calculations, cryptographic functions, just like SHA 256, and they're trying to get into a specific output. I'm sorry, my hand is falling down. Sorry about that. So this is a miner's obligation that they're trying to compute blocks. So every user that makes a transaction, they send those transactions to the miners collect them, they create a block, they mine it, and they publish it into the blockchain. Now, let's move into the proof of stake. I'm just covering the basics of the consensus protocols because I want to dive into the attacks in greater detail. If we need to go over something later, we will just include it there. Proof of stake, it's the solution to the huge energy consumption that occurs from proof of work. Proof of stake is being used by Peercoin and Nextcoin. Now, these were the first implementations of a proof of stake protocol, and they had the most faults in them, and the protocols are still maturing. We're still anticipating the Casper implementation and the Ouroboros for Cardano, which are going to be the next proof of stake implementations. For Casper, it is going to be a hybrid between proof of work and proof of stake. In proof of stake, we anchor the security of the network into the virtual world, which means that we're actually using the currencies of the system instead of just mining and consuming electricity power. Each user of the network can be a validator. This validator will need to have a certain number of tokens into that currency. For example, for Casper, Ethereum's release, they announced that the amount needed to be a validator will be around 1,500 Ethereum. This is around 1 million USD. So it's a pretty hefty amount. Now, validators, once they stake that amount, which means that they're going to freeze it with some specific opcode, they will not be able to retrieve that money. And by ensuring and staking that money, they're actually telling the network that they're trustworthy. And they will take the transactions from the users, they will include it in the block, and then publish it. Now, this process is completely randomized. Each user who has a stake is included into a pool, which we call the validator pool. From this pool, at every epoch, at every time frame that a block is needed to be mined, they will select one of those or a group of those, and that validator will mine the next block. We also might have the case where a validator just doesn't have enough transactions, and the block in that specific time frame is voided. It's null, it does not exist. Now let's head on straight away to the security of those protocols, and we're going to start off with double spending attacks. Double spending attacks, it's the major concern in the blockchain. It actually boils down to how can I spend one coin 2 different times, but the exact same coin? If you try to think of that in the real world, this won't work. You can go into one shop, use the same coins to buy something, and then go to another shop, and with the same exact coins, which you just gave to the other shop, buy something different. This simply cannot operate. But in the blockchain, if we think the longest chain rule, we can actually do that. We can have 2 competing blocks containing a different transaction with the same coins. Now, let's start off with the race attack. Race attack is basically a naive implementation of a vendor's API. When I'm buying something with cryptocurrency, the vendor needs to be able to have a way to know that I actually transfer that money to the vendor. So let's say that I'm adding the transaction to one block. It is mined. It is on the blockchain. But how does the vendor knows that the block is on the main chain and it's not just a branch? What if it's on that branch? It is on the blockchain. It is there. Someone did the transaction and a miner actually mined the transaction. But it's not part of the main chain. So in order to encounter this problem, the vendor will have to wait. We'll have to wait for some number of confirmation, some time. Now, what is a confirmation? A block confirmation is the number of blocks that are being built on top of the block that contains our transaction. For example, this block is an orphan block. There is no other block on top of that. So it has 0 block confirmations. But on the other hand, this block right here has 1 block on top of that, which means that that block has 1 block confirmation. If a vendor was accepting transactions with 1 block confirmation, it would accept this one to be true. But as we can see, this branch is not on the main chain. So this branch is not valid. If I, the vendor, was accepting 1 confirmation, I would be able to be duped and be a victim of that kind of attack. So the solution to this issue is to actually calculate the cost of the product that you're selling and try to stabilize and wait enough time for it to be correct. You want to ensure that the transaction will be on the main chain. For Bitcoin, the recommended amount of confirmations is 6. And if any one of you has ever used a crypto exchange like Binance or HitBTC, you would have seen that the number of confirmations rises up to 30. You would have to wait for 30 blocks before your transaction is considered as valid. Now let's move on to 51% attacks. They're also known majority attacks. Those terms are both used equally. In this attack, one entity of the network has the majority of the hashing power. If you think about it, the Bitcoin network right now has around the same computational consumption as Switzerland. It's a huge network. So in order to do a kind of attack like that, you will need to have another country's electricity consumption just on your own, just to start the attack. So for this attack, what we do is we own the majority of the hashing power, and we start to actually fork the blockchain. This is the point, it's not the Genesis block, this is the point where we actually contain the majority of the hashing power, and we start to mine our own branch. Since we have the majority of the power, at some point in the future, we will be able to outpace the main chain. With red, it's the malicious one, and green is the honest chain. And due to the longest chain rule, once we reach that point, the honest nodes will just think, which chain is the main chain? This looks like the longest one, so I'm gonna start mining on that chain. And this is how you actually do this attack. Now, going for a 51% attack, it's quite difficult. It is too expensive. You need to have too much power to do that. You may be able to do this through a mining pool, which is me as an individual. It is very hard for me to actually mine Bitcoin. It is very difficult for me to do that. I can't do this with my phone. I can't do this with my computer. I will need to have specialized equipment. So even if I do have this specialized equipment, I will need to join a network of other miners and combine our hashing power into getting some rewards. In case a mining pool, all the mining pools at some point in their life, they were close to the majority of the hashing power of a specific blockchain. And in all those cases, the network, the actual miners, the community, coordinated and they just left that blockchain, that's a mining pool. And they diverted into a competitor in order to stabilize the percentages. Because we don't want to be part of an attack, because we don't know what kind of history they're going to change. Now, a 51% attack can be discovered very quickly. You can see it, because it's going to take over the main chain, and we're going to see an example right now from Verge, which was discovered in less than 3 hours. Actually, in 3 hours, they actually made a hard fork of the chain, and they changed the issue that was there. Verge happened around 1.5 months ago. It was an attack on the network, and it is actually the only double spend attack that was confirmed. In this attack, the adversary actually discovered a bug in the block creation process, and they were able to actually dupe the algorithm and make and produce many successful blocks in a row. So in essence, even though they didn't have the computational power to outperform everyone else, by exploiting that bug, they could actually produce more blocks. And this gave them the advantage. And as such, it is a 51% attack. Now, the adversary got away with 250,000 Verge tokens. I think that was, at the time, it was around 1 million. I don't know if it was more. And in less than 3 hours, the Verge development team came up with an update. They had to hard fork the chain, and every miner that was supporting the blockchain had to update in order to continue mining into the blockchain. Another example is Electroneum. Electroneum 51% attack, it was around the same time as Verge. It is not confirmed, which means that it wasn't successful. It was identified that one of the mining pools, Bitmain, was close to the majority of the hashing power. And this is a very good indicator that something is going to happen. At the same time, there was a spike in orphan blocks. Orphan blocks, it is the branches that we saw earlier in the chain. When we have too many branches in a short period of time, it means that either something is going very wrong or an attack is going on the network. The last example that I have about 51% attacks, it is for Monero. That was actually the last week, the last 2 weeks, and it was a period in time where we've seen a spike in orphan blocks. So it's the same thing. You actually see too many blocks competing with the main chain in a very short time frame. What is interesting about this case is that one specific branch was 21 blocks in length. So for 21 blocks, the branch was competing with the main chain. If you remember the race attack we saw earlier, if you had any implementation and you were accepting transactions with less than 20 confirmations, you would be a victim of this attack. The first block of that branch, since it was 21 blocks in length, it had 20 confirmations. 20. That's a lot. The reason for this occurrence, it's either a desynchronization issue. Some blocks actually were left back in time, were desynced, and they started mining a different chain, which makes sense. Another case, it's all attacks. It is either 51% attack, trying to double spend something, or it was a selfish mining attack. In the selfish mining attack, the adversary actually mines blocks and do not publishes them into the network. It is some kind of form of denial of service, in the sense that the adversary will actually publish the mined blocks, which are not private to him, when the honest nodes will try to publish the valid blocks. In both cases, the blocks are valid, but the adversary actually hides the blocks up until both work? Great. At which point did you lose me? Well, should I go over this slide again? Is it all right? Cool. Now let's move on to long-range attacks. Long-range attacks is the greatest problem of proof-of-stake protocols. And it is the greatest problem because we have something that we call weak subjectivity. Weak subjectivity is the notion that a new node that enters the system and starts to mine the blockchain or just monitor it, or a node that was at some point alive and had an up-to-date version went offline for a few months. When they come up again, they're presented with different alternative branches. So as a new node, when you enter the system, you might encounter just a Genesis block, which is always the same, and then you'll be presented with different branches. They could be the same length. So weak subjectivity refers to the notion that we don't know which branch is the correct. We do have the longest chain rule, which means that the longest chain probably will be the correct one. But what if we have two chains with the same length? How do we identify that one of them is honest, one of them is malicious? In proof of work, it is very difficult to come up with a new chain. It is very difficult to actually mine a different chain and bring it at the same length with the main chain. Yes?
Just a quick question. Maybe I'm not the only one who's missing this. What is the condition for the branching to occur?
The condition for what?
For the branch to occur.
For the bridge. It's just an occurrence on the network. Two miners might at some point find the same block, but it could be just chance.
So it's unpredictable.
It is unpredictable. It could be an attack, or it could be just a random occurrence. In every time slot, every miner could start mining a block, but there is a chance that two miners actually manage to find a block at the same time frame. Both of those blocks might be correct, but in that case, one of them will be chosen to continue the main chain.
So there is no way to perform any particular action for the branch to occur?
No, you can actually predict that. It's a random thing. But if I go back into a specific block and I start mining that block, I can make a fork. So let's say that we're here and this is the main chain, and I decide that I want to do an attack on the network, and I want to revert transactions in this block. I'm going to go back to this one and start mining and create a new branch. And if I manage to make this branch longer, I will outpace and I will outlive the main branch. So it could be an attack, and it could be a random situation. All right. Now, another thing about proof of stake is that because we don't use any computational power to mine the blocks, we can actually create any alternative history with no cost. We consider the computational resources needed for mining a block to be minimal. So this is the solution that proof of stake gives. You don't need to compute. So just trying and make a different branch, it's very easy. It's very quick. So this is a real issue in proof of stake. Now, we have several different cases of a long-range attack. And a long-range attack actually refers to the fact that an adversary tries to go back in time, tries to go back into the Genesis block and start to mine their own alternative history. This attack is also known as alternate history, history revision, or just long range. There are three different cases. We're going to start with the simplest one, and we're going to just build up on difficulty. In this case, this is the Genesis block right here, and we have three validators in our pool. It is Bob, Alice, and Mallory. Each validator has the same chance of being elected and has the same stake on the network. So let's say it's just 1/3. Now, for these cases, we see a random distribution. Bob has 1 block, Alice 2, and Mallory 2. Mallory will want to do the attack on the network. So Mallory will go back in the Genesis block and will start to mine blocks on her own. The trick to this scenario is that the information about the validators and the chance that they have to produce the blocks, it is enclosed in the Genesis block. So even though Mallory will go back in time and will start mining the blocks on her own, she will not be able to beat the chances. She will always have the 1/3 chance that she had on the main chain. For example, we see here 5 blocks and Mallory has 5. So let's say that you have 2/5 to get 2/5 to get 2 blocks in 5 blocks. In her own chain, she will have the same chance. So in the time frames that go by, Mallory will have the same exact chance to get a block. The other chances are for Bob and Alice. But since Bob and Alice are not part of the attack, those blocks do not exist, are forfeited. In order for Mallory to do this attack, she will have to go into the future and mine blocks. She will have to spoof time. So in essence, yes, Mallory can perform this kind of attack, but in order to do that, she will have to actually compute blocks with future timestamps. In a naive implementation of a proof of stake, this might be correct, this might be all right. But all the implementations right now, they do check for timestamps. So this one will be rejected. So Mallory is seeing that it is very difficult to do this attack because she is limited by the stake that she has on the network. She will try to do something more. Now we'll go to the concept of validator rotation. We have the validators on the system, just Bob, Alice, and Mallory. Each of those validators, at some point, they retire. This could be after 1,000 blocks, could be after 5,000 blocks. We don't know. It's up to them, or it's up to the network, depending on the protocol, how it is implemented. Now, the validators, when they are active and they work on the blockchain, they do have some stake. They're invested in the blockchain. But once they are retired, probably they don't have any stake at all. They could just cash out, leave the network, go for vacation. In that sense, they don't pay attention to their keys. Their security hygiene is no longer the same because there is no stake. They have nothing to lose. So Mallory has two choices. One of them is to just hack Bob and get his private keys. And the other one is to bribe Bob. Bob right now has no stake, has nothing to lose, and can take part in an attack. So if Mallory says, hey, do you want to do this attack for me? Your key is valid. for the first 1,000 blocks. Bob is not capable of producing any new blocks on the system, but Bob can rewrite blocks for the first 1,000, 5,000 blocks that he was operating. So this is the posterior corruption attack. It is when you use no longer valid validators' information to rewrite old blocks. Now, let's go to the stake bleeding. This is very fresh research. I think it's less than 5 months. It is from the Cardano Research Department, IOHK. And it's very interesting. Let's say that we still have Mallory trying to do the attack. We also do have Bob and Alice on the blockchain, on the validator pool. They all have the same chance to produce a block, 1/3. Now, Mallory will have a copy of the blockchain locally and will continue being part of that blockchain. At every chance Mallory gets to publish a block, she will forfeit that. She will not mine the block on the main chain. With that sense, Mallory is trying to stall the blockchain. It's trying to make the blockchain grow slower. Because if you don't publish a block, there is no block. The length of the blockchain will be the same as the time frame before. Now, in the private blockchain that Mallory is mining is the sole stakeholder, has the same chance to produce a block. So as we saw before, it is slower at the beginning. Yes, I'm sorry.
What happens with the blockchain if Mallory she doesn't produce the block?
They're going to bring a mic, sorry.
Okay. What happens with the blockchain if Mallory just doesn't produce the block?
This depends on the implementation of the blockchain.
In general?
In general, they're trying to enforce some liveness conditions. Like if you don't mine a block when you're given the chance for like 5 times, you're being removed.
And this right is given to the other participants?
Maybe you're being removed from the validator pool, like you can no longer be the validator.
But for this exact transaction, the blockchain will wait for some time and then give this validator rights to the other participants?
Yes, no. For a specific time frame, one is being elected. If that validator does not publish a block, the time frame is being left void. So we proceed to the next time slot, next epoch. For this case, it's again an IV implementation where they don't have this condition. For this scenario, if someone doesn't publish a block, the blockchain continues and the algorithm continues as normal. So Mallory actually stalls the blockchain, does not publish a block, and the blockchain continues to grow slower. In her own blockchain, Mallory mines every chance she gets. So having the rewards of the system when you mine successfully a block, and taking into consideration transactions and fees that all the transactions have some, the stake is increasing with compound interest. Let's think about that. When you mine a block and you gain some rewards from the system, the reward is adapted into your stake, the stake increases, and your chance to produce the next block are actually higher. So, in essence, Mallory in her own blockchain will start very slowly and will accelerate very fast because she is the only validator that produces blocks, and will try to actually copy the transactions from the main chain, and will include the transactions with the highest fees, probably, which are in her own favor. So we have main chain, where Mallory actually stalls, does not publish any blocks. Gradually, in the future, the stake of Mallory in the main chain will be lower. She doesn't get any rewards from the system, so it actually moves slower. The other validators get more rewards, so their stake increases, while Mallory's remains the same. In the alternative chain of Mallory, the case is that she gets more and more and more over time. In a simulation of 6 years of blockchain history, that kind of attack is possible. Mallory is capable of starting as a sole validator, just copying transactions from the main chain into the alternative chain, stalling the main chain, and progressing the alternative chain as fast as she can actually outpace the main chain and gain the majority of the stake in the network. So what happens when Mallory actually outpaces the main chain? She has the majority. She's right now one of the sole validators because all the other validators do not publish any blocks. The history is around the same. She has made her own transactions, her own double spending attacks. And just before she publishes the blockchain, she transfers the majority of the stake to the other validators. So the end result will be that Mallory has a longer chain than the main chain. The validators will have exactly the same percentages in both chains because Mallory, in her own history, actually diverted most of the stake to the other validators, so they won't notice that something is different. And we have the majority of the transactions being the same. Now, in this scenario, we don't have issues with future blocks. The blocks are up to date. We don't spoof time in this one. We don't need to attack previous validators. So it's a pretty cool concept. Now, solutions for this attack. One of them, which cannot be used solely, it's the longest chain rule. As we've seen, this is longest chain rule works, but we need something more. This is why we introduced the moving checkpoints. Moving checkpoints, it is what is used by most cryptocurrencies right now, most blockchains. And the concept is that the blockchain is actually mutable, and you cannot change the history up to the latest number of blocks. Let's say the latest 1,000 blocks. All right? So you cannot change anything before that. Anything before that, it's written in stone, you cannot change that. Even if you do an attack, you cannot change the history. The next countermeasure, it is key evolving cryptography. This is used to mostly counter the posterior corruption attacks, where the private key of a user is, every time it is used, it evolves and the previous keys are invalidated. So it won't be possible to make a connection and actually sign previous blocks in time. The next concept is context-aware transactions. This is every block has information about the previous blocks in the chain. But what if we could add this information to the transactions themselves? So every transaction inside a block will contain information about a point in history. So you can actually bind each transaction to a certain point in the past. In case an adversary tries to copy the transaction to another private branch, the transaction will not compute. The transaction will be pointing to another block in a chain that it is not the main chain, it points into a different chain. So there can't be any correlation between the transaction and the branch that is inside. The last case, it is the plenitude rule. This is the latest countermeasure that was identified by IOHK, it's the Ouroboros research team, and it is part of the Ouroboros genesis. The plenitude rule says something very simple. It says that when you go and perform a long-range attack, you start from the genesis block. And since the chances of you, the validator, are the same as every other validators, or referring to the stake that every validator has, you cannot actually have the higher chance to mine a block than the other validators. So the attackers always start with a lower chance of producing a block. In a bigger picture, the branches that contain the honest validators, the honest nodes, will have more blocks, while the attackers will have less blocks, because they always start with a smaller chance to produce blocks. Now, it is essential to say that in proof-of-stake systems, we consider as a rule that the majority of the nodes, at least 2/3, need to be honest. If more than 2/3, if 2/3 are dishonest, the protocol breaks. It does not work. So in this case, we think that the adversaries are at least 1/3. and as a result, they will be computing blocks in a lower rate. Yes, 10 minutes. All right, cool. Now let's move on to nothing at stake. Nothing at stake is the problem that it is very closely associated with long-range attacks. It is the lack of penalizing the validators when they're voting for different branches. So let's say we have a branch, and the validator has, actually have a picture, might be better. All right. This is from the Wikipedia of Ethereum for proof of stake. It is, I think it's pretty clear. We have two branches. One branch is the correct one is a side branch. For the first one, we have a 90% chance to be the correct one and to get a reward from the system, while on the other one, we have a 10% chance. Now, if we vote for the correct one, we have a 90% chance to get a reward, and the other one, just 10%. But is there any incentive that stops us from voting for both branches? If we can vote for both branches, we can actually maximize our rewards and get everything. So the nothing at stake problem actually says that. Since there is no penalty, why don't I vote for every possible branch, for every possible case? This way you get the most rewards of the system. Now, this kind of attack would not work in a proof of work system. In proof of work, we actually consume electricity to mine the block. So if we tried to mine into two different branches, we would actually splitting the computational power of our systems in half, which means that we'll compute the block in twice the time. So instead of maximizing profits, we'll get just 50% of the profits. Now, the nothing at stake, there are different solutions and different thoughts on how to counter and tackle this problem. The main one, the main solution is that validators will actually lose their position as validators of the system. If they're discovered to be voting deliberately on competing branches, they will actually be removed from the validator pool. If you're removed from the pool, you don't get the rewards. You don't have this authority over the system. And this is something to consider that it is a stake. If you lose your position, you don't have any power on the system. You don't get the rewards from the system. The next solution that was introduced by Casper, Ethereum, it is the slasher condition. The slasher says that if you're found to be voting for competing branches and you're trying to actually prolong both of them, you will have your whole stake slashed, which means that in Ethereum the stake is 1,500 Ethereum, you will lose all of that. It's a pretty good disincentive to not do any attacks. Now let's move on to the grinding attack. You may find this attack as pre-computing attack, but it's all the same thing. The pre-computing and grinding attack refers to a naive implementation again of the leader election process in proof-of-stake systems. As we said before, in proof-of-stake systems, you have a validator pool where every stakeholder resides in, and you pick one validator at every epoch. Now, if it was possible for one validator to predict the next validator, they could actually use that into their own advantage. This was actually the case for Peercoin and Nextcoin, where by computing and adding different transactions into the block and having a specific output, you could actually predict the next validator of the system. That was a naive implementation. It wasn't random, and it was associated with previous blocks. So in order to avoid this, the process of electing a validator for each epoch needs to be truly random, which is a very hard thing to do. Okay, it's almost done. So solutions for this problem, it's just to enforce randomness, to remove any links with previous blocks, and just hope that the algorithm is not broken in 5 years. The last thing we're going to see today is liveness denial. Liveness denial is when validators of the pool coordinate and try to actually stop the blockchain from progressing. It's actually what we saw in the stake bleeding attack, where Mallory was actually forfeiting blocks in order to stall the blockchain. This is a more organized attack, but it's the same concept. So validators come together and they stop producing blocks. This will actually terminate the blockchain. The transactions will never go through, will never be written on the blockchain. And as a result, the validators will not get any rewards of the system. Their stake will be the same. The value of the coin will be reduced, because if the blockchain does not work, what is the point of being a validator? What is the point of having the currency? And solutions for that would be to actually remove the validator from the pool. This can be performed by a hard fork, just introducing a new version of the system and remove all the validators from which do this kind of attack. Perfect. Yeah, and the last concept is that you require a condition of liveness for your validators, meaning that if they don't publish a block into specific time frames, they're being removed. And the other one is to actually rotate the validators every certain points, like 1,000 blocks, 10,000 blocks, or whatsoever. And I think this is the end of my presentation. If you have any questions,
That's an honorable award to Evangelos.
Thank you.
That's also yours. And now we're going to have questions from the audience. And Evangelos, you're going to have to pick three best questions, and we'll give like T-shirts and stuff.
Okay, great. Thanks.
Okay. My name is Ivan Ivaninsky, Smart Deck Information Security. Thank you for the great presentation. I'd like to ask the following question. I've heard about an attack on Bitcoin in the following way. The attacker tries to perform a double spending, but not by mining the blocks by him or herself, but by including a great fee for the miner in one of the blocks in the sidechain, making it economically profitable for miners to switch to the sidechain.
Okay.
The thing is that Bitcoin is a pretty well audited and a minimalistic system, and if we have such attacks in Bitcoin, we might assume that we will have many more sophisticated social attacks in other more complicated and less audited and more new blockchains.
Yeah.
Don't you think that the industry is moving too fast, and we are going to face these attacks, and they are going to perform really big harm?
Thanks for your question. Is it working? I think it's working. Yeah, cool. What you referred to is the bribing attack. I also have slides for that one, but I didn't have time. I have to remove that one. Yes, we're moving too fast as an industry, and the research on that field is starting to be more dense. We see more things all the time, and we see wonderful things. For example, it was the first case in history where we have a cryptographic research from technical paper to being into implementation in a very short time. I'm referring to Ouroboros and the IOHK research department, where they actually managed to find solutions to many problems for proof of stake, and actually move them from research, just theoretical research, to actual product. In essence, yes, we're moving very fast. We will see too many dangers in the future, and I hope that as a community we move forward to tackle them. Thank you. Any other question?
Thank you for the presentation. I have a couple of questions. Am I understanding right that one must to be a validator to do some kind of attack? And the second question, is validator a person, or it can be some pool, and how that pool can work?
The validator, in most attacks, it should be a validator or a miner. In the proof-of-stake systems, we refer to them as validators or as minters, while in proof-of-work systems, we refer to them as miners, because they actually do the computational work. In order to be a validator, you don't need to be a team. You can be a team. And in different cryptocurrencies or blockchains, they might require you to be a team. For example, in proof-of-authority protocols, we have seen the cases where they require organizations to be validators. So in that case, it is a team. It is a whole group of people being the validators. In the proof-of-stake, we refer to individuals, or more specifically to wallets. So you have the wallet has enough currency to give you stake into the platform, and you use that to actually be a validator. So it can be both cases, but it depends on the protocol. Thanks.
Yeah, thanks.
I'm sorry, is it the third question? Is the last question? Okay.
Okay, thank you a lot for the presentation. I have two questions. Maybe I missed something regarding the case when you described that the Alice or whoever this try to fork the blockchain with the proof of stakes on your own computer like this, with generating blocks and so on to do it, and missing the generation of blocks in the main chain. Mm-hmm. So I just don't understand the following. If she received the main chain and she just copies it, how she can generate blocks if chains are interconnected?
Chains cannot be interconnected.
They are just split.
In the blockchain, it's just one way. It's not connected. In the only case that chains could be interconnected, it would be in directed acyclic graphs kind of technologies, which is not the blockchain. It is a different type of distributed ledger technologies.
Okay, I see.
But for the blockchain, it is just one direction. You might have branches, but they're not being merged at some point.
So they are not anyhow, I don't know, connected with each other at all?
They just derive from the same parent.
Okay, so that's why it's possible to generate blocks in her own and to copy other blocks.
Yeah, exactly.
I see. And the other question regarding the validator rotation.
Yeah.
Am I right that the validator depends on the amount of stakes which you have?
Yeah. The chance of producing a block is proportional to the stake that you have on the platform.
So for each block, for each proof of stake blockchain technology, cryptocurrency, the validator is always rotated, or it may be hard-coded in the system.
At the first case, at the beginning of the system, it usually starts as static.
Okay.
Like it has to begin from somewhere, and then they rotate. So at the beginning, there could be just a fixed number of validators, known validators, but as the system progresses, the validators keep rotating.
Okay, but the
it
number
wouldn't
of
be fair to have the same validators all the time.
Okay, I see. But the number of validators in the system at the same time, I mean the number of valid validators which the system choose from.
Yeah.
There can be the thousands of.
This depends on the protocol. It could be different number on different protocols.
But how many right now cryptocurrencies? The last question: how many cryptocurrencies use the proof of stake right now?
Proof of stake is being used by numerous cryptocurrencies. The working implementations of proof of stake, it is from Peercoin, Next, and there should be another handful of them. But it's the protocol that is being implemented in Ethereum. It's going to be a hybrid of proof of work with proof of stake. And we're going to see it in the future quite often. It is the solution to proof of work. We want to reduce the environmental footprint that we have with blockchain, and this is how they actually manage to do that.
Hi. Well, my question is very short. it's about proof of stake, and you said it's proportionally how the proportionally to the miner's stake. And my question is how what's the way to choose the proper amount of stake to be a miner?
What is the proper amount of stake that you choose?
Yeah. How Vitalik choose the amount of stake equals 1 and 500 at ethers to be a miner?
To be honest, I don't know how to answer that. I think it's random. They just sat on a table and they just pick a number.
But can he choose it 1 ether or 10 or maybe it's 100?
They can, but they want you to be trustworthy. If it's a very low amount, you might have the flexibility to do attacks on the system. But if it's high enough and it's expensive for you, you won't be more honest.
For one people, it's
it's
cheaper. For another, it's expensive. It doesn't matter. Is there any mathematical right way to choose a proper amount of stake to be a miner?
I don't know about that, to be honest. It's just they consider a different number for its stake.
Okay.
Thank you for your presentation. So my question is about long-range attack. So there was a countermeasure that was based on setting the late checkpoint. And what's the problem of making this checkpoint later? So you said that there might be an amount of some stakes, for example, 10,000. What's the problem of making it a bit later? For example, when you see that one branch is main, from the point you see that it is main, you can set the checkpoint on that branch by some condition. So,
all right. This is when you actually enforce the time checking. You are removing every kind of long-range attacks. So what is left is short-range attacks. We didn't have the time to go into that, but short-range attacks refers to what you say, that you can always change the latest 1,000 blocks. Yeah, but in order to do that, you would have to go into a bribing attack, as your colleague referred before. A bribing attack means that the miner will have to bribe all the other validators into promoting his block. And you have a very high risk in bribing. Actually, I have the slide here. All right, this is the P epsilon attack. This is from one of Vitalik's posts regarding this attack. This is the bribing. You have two competing branches. The chance to, if everyone votes for one branch, you get this kind of reward, P, on the system. If the rest do not get anything, all right? But if you vote for the other branch, you do get the reward of the system. So in a bribing attack, what you actually do, you being the malicious node, you say to all the other nodes, please vote for my branch. And I'm going to give to all of you this kind of reward. So it actually matches the reward of the main branch plus something extra. Now, this is a no-cost attack because the adversary, if everyone votes for your branch, because it's a win-win situation for you. Even if you vote for one or the other branch, you do get something in return, all right? So everyone will vote for one. And the adversary's branch will progress, and the adversary will not have paid anything, because this is the reward from the system. So the adversary just bribed everyone with nothing. The problem is that you can do this, yes. This is a possibility. But if you build up, for every subsequent block, you will have to do the same. And for every block, you will have to bribe everyone with the same condition. Which means that if you go 100 blocks down further in the line, and someone decides, and you stop giving this bribe, everyone will just go back to the main chain. They could go back to the main chain, right? So in that case, you would have to pay to everyone the bribe for every single block. which makes it very expensive for you to do that.
So the answer is that the attack is really expensive, and there is the countermeasure of the checkpoint based on the length of maybe 10,000. It is sufficient right now.
It is sufficient to counter long-range attacks.
Okay, yeah, thank you. Understood.
Cheers.
Thank you for presentation. I have a question about existing implementation of proof-of-stake algorithms. If we look of all existing implementation, we can see that most of coin share controlled by developers of these systems, and this is reason why we can say that we have proof that this is secure. At Casper protocol also not will be implemented in pure proof-of-stake protocol. Also because Vitalik have no proof that this protocol will be secure. Ouroboros also released under control of IOHK, and how we can trust for proof-of-stake protocols in this situation.
I'm sorry, I missed the question.
How we can trust of existed released implementation of proof-of-stake protocol? We have no proof that all these protocols is secure.
Yeah, that's a very good question. The implementations that are out there right now, we're not certain for them to be secure, and Ouroboros, which is in the development phase, they're trying to counter every single one of those problems, and they're trying to, when they release, to be secure. But as a result, what we have right now, it's not either fully implemented, like Casper or Ouroboros, they're not operational. What we have implemented is Next, Bitcoin, and a few other cryptocurrencies, and we do have those problems, yeah. In those cases, we do have some kind of trust in the system. For example, for weak subjectivity, the issue we talked about that you don't know which chain to pick, it is solved by most cryptocurrencies, an example from Casper, from Ethereum, by ensuring some trust on the system. So when you download the software to be a miner, you have the Genesis block, but you also have which one is the main branch. I know it might not be ideal, but we do have some kind of trust.
Hello, thank you for your speech. I wanted to ask if you performed a long chain attacks and you have some blocks and you can put transactions in them. So what is the best way to make a good profit from that?
How do you profit with that?
Yeah. I mean, if you have proof of stake, so you probably have a lot of money, and if people will know that you made a good attack, the cost of currency will fall down. So the attack will be failed, in fact, and you lose money. If you have proof of work, you can just change the currency with your ASICs and so on. But there is a general way to make a profit from long chain attack.
You can actually, when you perform a double spend attack, you have a short period of time before the network identifies that the attack took place. So in that short period of time, you can just take the money, cash them out, and just be gone.
So you mean it is probably a good idea to use some exchangers in the attack?
Good idea. I'm not promoting you to do the attack.
But I am asking if I want to do the attack, what should I probably do?
There are multiple ways to do that, but an exchange is one choice, yeah.
And I wanted to ask, so is it probably a good idea to attack small coins that have small capitalization or big? For example, I don't understand how to do this, for example, with Bitcoin.
It will be easier to go for shorter blockchains. The cost is lower. The coins cost much less than Bitcoin.
So it is a good idea to attack small coins with and use exchangers for that, yes?
Smaller blockchains are easier to attack, yeah.
Okay, thanks.
3 best questions.
What is that?
You pick 3 best questions.
Oh. Ah. I thought it was just 3 questions. But one question goes there. Do I do something? I don't know what I do. I just pay.
You just point.
One question very good there. Another there. You take this. And one here.
Okay, and the best of them. Number 1 question. from this. Еще. Number 1 question.
Okay, I'm gonna go for yours because you gave us to explain that one.